So can you share the screen?
Mm-hmm.
Okay. So wait a second now. I forgot your title.
It's at the bottom of the screen.
At the bottom of the screen, I can read Seminario de Geometría No-Commutativa del Atlántico Sur, but not the title. Yeah,
no.
yeah. Okay. Okay, hope I'm not revealing too much by reading the title of the talk. So it's a pleasure to introduce Bernhard Keller from Paris SET, who will talk about singularity categories, Leavitt path algebras, and Hochschild homology. Please, Bernhard, go ahead.
Thank you very much, and thank you very much for the invitation. I'm very happy to speak here at the Non-Commutative Geometry Seminar of the South Atlantic. So my subject today is Singularity Categories, Leavitt path algebras, and Hochschild homology, and it is based partly on joint work with Wang from Paris and Nanjing, and with Umamaheswaran Arunachalam from Warangal, which is a city in South India. And the plan is as follows. I would like to start with the philosophy of non-commutative algebraic geometry, because it's perhaps a bit different from that of the non-commutative geometry, which you usually have in this seminar. Then I will have a reminder and a few compliments on Hochschild homology. Then I will write down complexes which allow to compute Hochschild homology of derived categories and of singularity categories. And finally, as an application, I will show that these complexes also compute Hochschild homology of graded Leavitt path algebras and of certain differential graded Leavitt path algebras. Okay, so let me start with the philosophy of non-commutative algebraic geometry, following the spirit of Greenfeld, Kontsevich, and others. So in this subject, somehow the basic question is, what is a non-commutative scheme? Yes, we all know what a commutative scheme is. It's a gluing of affine schemes, which are essentially the same as commutative rings. So what should a non-commutative scheme be? Well, there is one traditional answer, which goes back to Grothendieck, Gabriel, Manin, and others. And this answer says that it should simply be an abelian category, namely the abelian category of quasi-coherent sheaves on some hypothetical non-commutative space. And then every commutative scheme gives rise to a non-commutative scheme, namely simply its abelian category of quasi-coherent sheaves. Okay, now we are interested in these non-commutative schemes and in their homological invariant, and it turns out that the most essential homological invariants in which we're interested in for a scheme or its category of quasi-coherent sheaves, in fact, don't depend so much on the abelian category of quasi-coherent sheaves, but only on its derived category, which is no longer abelian, but still triangulated. And this then leads to a second answer to this question, which was advocated, among others, by Greenfeld and Kontsevich, namely, a non-commutative scheme should be a triangulated category, namely the derived category of the category of quasi-coherent sheaves on some hypothetical non-commutative space. And then again, each commutative scheme now gives rise to a non-commutative scheme in this sense, namely the derived category of its category of quasi-coherent sheaves. Okay, well, this is very nice as a philosophy, but when we try to put it into practice, we encounter serious technical difficulties with triangulated categories. And perhaps the most important one is that if we have a triangulated category T and some small index category I, then the category of functors from I to T, yes, the category of I-shaped diagrams in T is no longer triangulated. In general, yes, so this happens already for very small categories I, if we take for I this category, so that the functor category is just the category of morphisms in our triangulated category, that is no longer triangulated in for most T. Okay, and so the solution to these technical problems is to replace triangulated categories with differential graded categories. And well, there are too many differential graded categories. We have to consider them up to a suitable equivalence relation. And the equivalence relation which we use is derived Morita equivalence. Let me quickly define it. Well, we say that a differential graded functor between differential graded categories is a Morita functor if the restriction along this functor is an equivalence between their derived categories. And then we say that two differential graded categories are derived Morita equivalent if they're linked by a zigzag of Morita functors. And then non-commutative algebraic geometry becomes the study of small differential graded categories considered up to derived Morita equivalence and of their invariants like K-theory, Hochschild homology or cohomology, cyclic homology, and many others. So the rest, this is the background against which the rest of the talk should be seen. So, and before we come to that, yes, is there a question?
Yeah, a small question. Is the derived category a contravariant with respect to the DG category?
Well, you can view it either way. Here, just for the sake of the definition, it's easiest to view it as contravariant, but in the rest of the talk, I will usually view it as covariant. I mean, it is both. Since it's the unbounded derived category, it is both covariant and contravariant. Mm-hmm. So we always have the restriction functor, and it always has a left adjoint. I will usually use the left adjoint of the restriction functor.
Okay.
Okay, so, well, since this was all a bit abstract, let me show you concrete pictures of categories which resemble those which we would like to consider. Okay, so here you can see such categories. More precisely, these are pictures of the associated triangulated categories. And so even more precisely, the vertices in these pictures are the indecomposable objects in these categories. So in both cases, we have only finitely many indecomposable objects. And the edges, they should all be oriented in the same direction. The edges form the irreducible morphisms, which form a canonical generating family for all the morphisms between indecomposables. And since the categories are Krull-Schmidt, this determines the category at least as an additive category. And then they are triangulated. So in particular, they have a shift functor, a suspension functor. And in this case, the suspension functor is just the shift by one unit. So this would be an orbit under the suspension functor. And so you see that suspension functor is periodic, is finite order up to isomorphism, and that's also a typical phenomenon which occurs in singularity categories, which we will see. So here, yes, so here you see the one, okay, these are actually cluster categories, whatever that means, associated with Dynkin diagrams E6 and A15. Okay. Okay, so now let's remember the basics of Hochschild homology. We work over a field for simplicity, and we consider K algebras. By a K algebra, I will always mean an associative K algebra with a unit element, but usually non-commutative. And I will write capital mod A for the category of all right A modules. And then I will write D of A for the derived category of this abelian category, the unbounded derived category. So its objects are all complexes of right A modules, and its morphisms are obtained from morphisms of complexes by formally inverting all quasi-isomorphisms. Okay, and well, we are interested in bimodules, in particular in the bimodule A, which I will call the identity bimodule or the diagonal bimodule. And we view bimodules as modules over the so-called enveloping algebra, the tensor product of A with its opposite algebra. And then, if we like, we can define Hochschild homology using the Tor functor applied to the identity bimodule with itself. And if we use the bar resolution to compute this Tor functor, then we get the Hochschild complex, whose homology computes Hochschild homology. Here I've only written down the last differential, yes, which is perhaps the most important one. You will remember the others. And you then what we see is that in degree 0, we obtain the trace space of A modulo the subspace generated by all commutators. We see that Hochschild homology and in fact the Hochschild complex are functorial in A with respect to algebra morphisms, even algebra morphisms which don't preserve the unit. And we will usually consider these complexes, the Hochschild complex, as an object of the derived category of vector spaces. So whenever we have a quasi-isomorphism, we will consider this an isomorphism in the derived category. Okay, and now this definition extends easily from K algebras to small k categories, script A. For example, then the Hochschild complex becomes this complex. Yes, in degree 0, we put the direct sum of all the endomorphism algebras of all objects of our small k category. In degree homological degree 1, we put this tensor, this direct sum of tensor products. Yes, we can view the tensors as diagrams like this, and then the differential is given by the same formula, now interpreted in a slightly different way. The elements, well, yes, the elements of the term in degree 2 are sums of such diagrams A, B, C, etc. Okay, and then we can in particular apply this Hochschild complex for categories to the category of finitely generated projective modules over our algebra A. And well, we have an obvious inclusion from the one object category given by A to the small category given by the finitely generated projective modules over A. And this inclusion functor induces an isomorphism in the derived category, as it's not easy, not hard to see. And this then yields Morita invariance of Hochschild homology and the Hochschild complex. Now the definitions extend further to differential graded K categories. Yes, for example, as our differential graded category, let us take the category now of bounded complexes, yes, bounded complexes of finitely generated projective modules. So objects of this category are just such complexes, and instead of morphism vector spaces, we have morphism complexes. If we look at two such complexes, the nth component of the morphism complex between them is formed by the A-linear homogeneous maps of degree n between P and Q considered as Z-graded objects. Yes, so this F, this does not see the differential, this definition of the components, but the differentials enter in the definition of the differential of this morphism complex. It's the supercommutator with the differentials of P and Q, which gives us the differential on the morphism complex. Okay, now whenever we have such a DG category, we can form its H0 category. It's the category with the same object and whose morphisms are now ordinary vector spaces, namely the H0 spaces of our complexes. And in this case, what we get is the category up to homotopy of complexes of finitely generated projective models. And there's a question. Yes.
Yeah, I saw two raised hands and some question in the chat.
There's a question in the chat. Let me see. Are there any obstructions in extending this definition of HH to topological algebras? I think there are none if you use the proper tensor product. But I think there are people in the room who are much more competent for answering this question than myself. Okay. Yes.
Yeah, well, with completed projective tensor product, you can do it. But then, I mean, there are lots of variations of things that you might want in the analytic setting. So.
Yes, thank you. Yes, sorry. Since I'm in the algebraic setting, there are no topologies on my algebras. Okay. Yes, so we have this nice DG category associated with our algebra A. And then we can view each finitely generated projective module as a complex concentrated in degree 0. And then we can view this category itself as a DG category concentrated in degree 0. And we have an inclusion factor to the DG category of bounded complexes of finitely generated projective modules. And this inclusion factor, again, yields a quasi-isomorphism, so an isomorphism in the derived category of vector spaces. And from this, we can deduce Morita invariance of Hochschild homology. Well, derived Morita invariance, even something a bit stronger. We can even start just from a triangle equivalence between two algebras, A and B. So here it's important that A and B are concentrated in degree 0. And we just take a triangle equivalence. And then by a theorem of Ricard, just the existence of a triangle equivalence implies the existence of a zigzag of actually quasi-equivalences, in particular Morita functors between the two. And and this then, as you can easily deduce from this, implies isomorphism in the Hochschild complexes. Yes. So this is somehow an exceptional situation where the existence of a triangle equivalence suffices. I mean, if we take for A and B DG categories, then we have to assume the existence of a zigzag of Morita functors. Okay. Yes.
So let's take B are algebras, right?
Pardon?
A and B in the result of Ricard that you stated. A and B are algebras.
In Ricard's result are algebras concentrated in degree 0.
Yeah, and so your remark is that this doesn't hold for more general DGCATs.
This doesn't hold, for example, already for differential graded algebras. Yes. Okay. Yes. Now, well, I have not yet defined what the derived category of a DG category is, so let me do it now. So the category which generalizes the category of complexes is the category of differential graded right A modules. And well, these are just the differential graded contravariant factors with values in the differential graded category of vector spaces with the analogously defined morphism complexes. And then the derived category is obtained by localizing this analog of the category of complexes at all quasi-isomorphisms, where quasi-isomorphisms are defined pointwise. Okay, and once we have this definition, we can formulate a localization theorem. Let's take A, B, C, an exact sequence of DG categories. But what should that mean? Well, it should mean that if we pass to the derived categories and use the left adjoints of the restriction functors, then we have an exact sequence of triangulated categories in the sense of Verdier. So D of A should identify with a full triangulated subcategory of DB, and the Verdier quotient of DB by the image should identify with DC. Okay, and such a sequence then yields a canonical triangle in the derived category of vector spaces, and sigma is my notation for the suspension, which most people denote by this 1 in brackets. Yes, so it shifts the complex to the left and changes the sign of the differential. Okay, and now this was all very general. Let's now come to something much more specific and concrete. Let us take a finite quiver, yes, so a finite oriented graph, and let's take its path algebra. Yes, I think I don't need to recall what the path algebra is. If I should, please let me know. And we take a quotient of the path algebra, A, which is itself a finite dimensional quotient. So we assume that we have a finite dimensional quotient by an admissible ideal. So this admissibility means that the ideal contains a sufficiently high power of the ideal generated by all arrows. So that will ensure that the quotient is finite dimensional. And then we also assume that this presentation of our algebra is in some sense minimal, in the sense that we cannot eliminate arrows using relations, and that is ensured by the condition that I should be contained in the square of the ideal generated by the arrows. Q1 is the set of arrows. Okay, and then we will need the following result by Michel van den Berg from 2015. It tells us that the Hochschild homology of the Kossel dual of our algebra A is just the K dual of Hochschild homology of A. And I should recall the definition of the Kossel dual. Yes, it's the derived endomorphism algebra of the sum of the simple A modules. So R here is the quotient of A by its Jacobson radical. And this quotient, well, since we have taken such a quotient, this quotient by the radical identifies with the sum of the simple modules, which are all one-dimensional and attached to the vertices of our quiver. Okay, so this allows us, yeah, a nice duality formula. Let me illustrate this on an example. Yes, so in case you're not familiar with the Kossel dual, maybe this is helpful. So a typical example would be the following one. We take this quiver with 3 vertices, and between any 2 consecutive vertices, we take 3 arrows labeled x0, x1, and x2, like homogeneous coordinates in the projective plane. And then for our ideal I, we take all the commutativity relations. So x0 composed with x1 should be equal to x1 composed with x0, for example. Yes. And then we get the quotient is a certain finite dimensional algebra, which is actually, whose derived category is actually equivalent to the derived category of sheaves on P2, quasi-covariant sheaves on P2. Okay, and then it is not hard to compute the Kossel dual in this case. So to compute the Kossel dual, we reverse the arrows in our quiver, and we give the degree +1 to all the reversed arrows. And we impose anti-commutativity relations between these reversed arrows. So this will, then we have the corresponding graded path algebra, which will be, which will still be finite dimensional, of course. And it's a graded algebra, and we endow it with the zero differential. And then it is not hard to check that this construction actually does give a realization of the derived endomorphism algebra of the sum of the three simple modules over our algebra A. Okay. Yes, so I think it's quite nice as an example illustrating causal duality. From the point of view of Hochschild homology, it is not so interesting because actually Hochschild homology of this algebra is trivial. Yes, reduced Hochschild homology vanishes. Yes, in degree 0 we just have it is concentrated in degree 0, and in degree 0 it is generated by the three idempotents associated with the vertices, and the same of course then for the dual, for the causal dual. Are there questions so far? Okay, well, if that's not the case, let's go to the next section. So now I would like to write down complexes computing Hochschild homology of the derived and the singularity category of such an admissible quotient of a path algebra. Okay, so we take again such an admissible quotient, in particular it's finite dimensional, and we look now at the category of its k finite dimensional right modules with a small m, because now the modules are small, they are finite dimensional. Okay, and then we have the corresponding bounded derived category of the module category. So now the objects are bounded complexes of finite dimensional A modules. And inside we have the perfect derived category, where we assume in addition that the components are projective, or in other words, we can say that it's the thick subcategory generated by the free model of rank 1. Yes, so this is a thick subcategory of the bounded derived category, which is equivalent to the category up to homotopy of bounded complexes of projectives. Okay. And well, since we have such a thick subcategory, we can form the Verdier quotient, and this is known as the singularity category of our algebra. It was first considered in this context of non-commutative algebras, possibly infinite dimensional, by Buchweitz in an unpublished manuscript in 1986, and it was rediscovered by Orlov in a geometric context linked to mirror symmetry in 2003. And Orlov showed that the corresponding quotient for a scheme, yes, you take coherent sheaves modulo perfect complexes of coherent sheaves modulo perfect complexes of coherent sheaves. This quotient only depends on the singularities of your scheme, and that's why it is nowadays usually called the singularity category. Okay. So by definition, we have an exact sequence linking the singularity category, the bounded derived category, and the perfect derived category. And all these categories have canonical differential graded enhancements. Yes, the canonical differential graded enhancement of this category is the DJ category of bounded complexes of finally generated projective modules. And there are similar canonical enhancements for the derived category and for the singularity category, because in fact, whenever you have a localization of a category with a DG enhancement, then the localization inherits a canonical enhancement. Okay. And so this is, if you like, you can even use this to define the DG singularity category. And now we can apply the localization theorem to this triangle. Okay, so we get such a triangle in the derived category of vector spaces. Now the left-hand side by Morita invariance, and this term also identifies with Hochschild homology of A. And so to find this term, well, we first compute this term. And the claim is that this term identifies with the dual of Hochschild, the K-dual of Hochschild homology of A. Okay, and the proof is not hard. Let me sketch it. Yes, so remember we have introduced R, the sum of the simple modules, and its derived endomorphism algebra, which is just the causal dual. Now, the sum of the simple modules is a generator for this triangulated category. And since so we have a Karoubian small triangulated algebraic triangulated category, and we have a generator, and then the Hom functor associated with this generator gives us an equivalence with the corresponding perfect derived category of the endomorphism algebra. And this, well, this is a priori, this is at the triangulated level, but it lifts to the DG level. Yes, this type of functor easily lifts to the DG level. And then we get, then we get induced isomorphisms in Hochschild homology. And by Vandenberg's theorem, Hochschild homology of this causal dual is the dual of Hochschild homology of A. Okay.
Yes. Just a question. What's the map? How do you map? I mean, according to this, there is a map from HHA to its dual.
Absolutely, yeah, and I will give you this map in a second. Yes, okay. Absolutely. Okay. Yes. Yes, so let us abbreviate the DG singularity category by script S. Okay. And so now what I'm claiming is that this DG singularity category, sorry, the Hochschild homology of the DG singularity category is isomorphic to what I would call the double Hochschild complex of A. So we take the Hochschild complex of A in degrees -1, -2, etc. And we take its dual in degrees 0, 1, etc. And the two are linked by a kind of trace map. So how does it work? Well, we take an element of A and want to define a linear form on A. So Tor of A applied to an element little b. Well, we define this as the trace of left multiplication by A composed with right multiplication by B. Yes, and since our algebra is finite dimensional, this endomorphism has a well-defined trace. And so we get a linear form on A, and well, it's easy to see that we actually get a complex in this way. And well, okay, this map is also identifies, of course, with this map. Yes. Okay. And yes, so we get a very nice and simple expression for Hochschild homology of this singularity category. In particular, all the different homologies are finite dimensional. Yes, they are homologies of a complex with finite dimensional components, which may be a bit surprising because in general, this category or the singularity category itself, the H0 of this category, has infinite dimensional morphism spaces. Yes. Okay. And as a corollary, we get isomorphisms, of course, well, between Hochschild homology of the singularity category and Hochschild homology of A in degrees n greater or equal to 2, and a duality with degrees in the other direction, and in a duality between degree 1 and degree 0. And we can generalize, if we like, this theorem from finite dimensional algebras to suitable proper differential graded algebras. So a differential graded algebra by definition is proper if its homology is of finite total dimension. Okay. And now there is a link to Leavitt path algebras, which I would like to exploit now to compute Hochschild homology of certain graded Leavitt path algebras. So again, we start from a finite quiver, for example, this one loop quiver. And then we look at the associated radical square zero algebra. So that's the quotient of the path algebra by the ideal, by the square of the ideal generated by all arrows. Yes, so in this case, this will just be the algebra of dual numbers. So in general, yes, any non-trivial product in this algebra is zero. So, and now we introduce Q star. Well, as in the example, it will be the opposite quiver. And we give degree +1 to all of its arrows. So here for the one loop quiver, it's just the one loop in the other direction, now called epsilon star. And well, to define the associated Leavitt path algebra, we do the following thing. Let us fix a vertex of our quiver and consider all the arrows which go out from this vertex. Yes, so we number them from 1 to ni, and for each arrow we have a certain target of this arrow. And now we look at pi, the graded right module associated with the vertex. Yes, ei is just the idempotent given by the vertex I, by the path of length 0 at the vertex I. So this is a finitely generated projective right module of the graded path algebra of this quiver. And then left multiplication by the arrows gives us this morphism from pi to the sum of the shifts of the projectives associated to the targets of the arrows. Okay. Yes. Okay. So in our example, well, we have only one arrow, and so we only get this arrow of degree +1, or arrow of degree 0 between P1 and its shift, given by left multiplication. Notice that if there are no outgoing arrows at the vertex I, if I is a sink of our quiver, then this sum by definition is 0. So then we would get a 0 target here. Okay. And now to define the Leavitt path algebra, we introduce formal inverses of these morphisms. Yes, so these are columns. Now their inverses will be rows. And so we impose on the beta i's, we impose the relations which tell us that this matrix is inverse to this matrix. Okay. And then the associated graded Leavitt path algebra is just obtained by adjoining the coefficients beta ij of these formal inverses to the graded path algebra of Q. Okay, and that this localization inherits a grading, and we can endow it with the zero differential. Yes, so in this very simple example, it is just the Laurent polynomial algebra in one indeterminate. But this example is really exceptionally simple. In general, it is infinite dimensional in each degree. Here, exceptionally, it's finite dimensional in each degree, but in general, it is infinite dimensional in each degree. And what is the link to the singularity category? Well, this goes back to work of Paul Smith, and in the differential graded setting to work of Xiao-Wu Chen and Yang, published in 2015, the DG singularity category of our radical square zero algebra A identifies with the perfect derived category of the Leavitt, of the graded Leavitt path algebra. We just send the projective at the vertex I to the simple module at the vertex I. Yes, this is certainly a finite dimensional module, and so gives us a well-defined object in this quotient. Okay. Okay, are there questions on these constructions? Okay, yes.
I was thinking this, so the fact that the Leavitt path algebra is has homological dimension 1.
Yes, it does not. Yeah, it doesn't really appear. I think, yeah, it's not so. I mean, of course, it is linked, of course, to the fact that the algebra A has radical square 0, but I think that let me see. I think it's not immediately. One cannot recover it immediately from this equivalence, as far as I can see. Yeah.
One little question.
But by the way, of course, the grading on the left-hand side. So here we have a grading shift on the left-hand side, which corresponds to the suspension factor on the right-hand side. Yes. Sorry,
there is a question in the chat.
Sorry, let me have a look at the chat. Let me see, where is the chat?
I can read it.
Yeah, I think I found it.
Okay.
Is the shifted duality for HH for the category SGA coming from some duality on the singularity category? Yeah, that's a good question. Yeah, it's a good question. Yes, so can we lift it to some duality for the singularity category? I don't see the answer now. Yes. No, a good question. I will try to think about it and let you know if I find something. I can't say anything like that off my head. Yes.
One question that I have: if you take the tensor product of two Leavitt path algebras,
it will no longer be a radical square zero algebra. So it will, yeah. But it will still, of course, be a finite dimensional algebra, and so what I'm going to say in a minute will apply to it. But it's yeah. Okay. Yes. So we have this equivalence, and therefore Hochschild homology of the graded Leavitt path algebra as well is computed by this double Hochschild complex. Yes, the double Hochschild complex computes Hochschild homology here on the right-hand side, and we have an equivalence up to Morita equivalence of DG categories, and so we have the same computation on the left-hand side, and in particular Hochschild homology of this graded Leavitt path algebra is finite dimensional in each degree, which is not clear a priori because, as I said, the Leavitt path algebra itself will be infinite dimensional in each degree, and in almost all examples. And then, of course, the computation of Hochschild homology of Leavitt path algebras is not new. Yes, it goes back to the work of Pereira and Guillermo Cortinas in proceedings of the AMS in 2015. But this is, I think, a rather different way of presenting the result.
So you present, so your grading corresponds to the grading of the algebra.
The grading, yes, I mean, here, yes.
Because you consider it as a graded algebra with
yes, the grading on the Leavitt path algebra is a homological grading. Yes. So I have to, yes. Yeah. I don't distinguish between. I mean, of course, one should do something finer and distinguish the two gradings, but in this theorem, in this corollary, the two gradings are mixed, are identified. Yes.
I mean,
the grading on the Leavitt path is a homological grading. Yes.
But in the paper you cited, we have HH0 and HH1, and the rest are 0.
Absolutely. Yes.
But if you take into account the C grading, that's different.
If you take the grading, if you take this grading, then you should get this. Yes.
Yeah, because I mean, just to point out that in our paper, our HH0 and our HH1 are not in general finite dimensional, but each of the graded pieces is.
Yes, absolutely. Each of the graded pieces. Yes. Okay. More questions or remarks? Well, then let me look at the case of a more general algebra. So we now still take a finite quiver, and we still take an admissible ideal. So we have the finite dimensional quotient. And now we consider R as a subalgebra of A, simply the subalgebra generated over K by the idempotents associated with the vertices. And then the algebra A becomes, let's say as a vector space, as an R bimodule, actually. As an R bimodule, it becomes the direct sum of R and the radical in a canonical way. And what we can then do is we take the tensor algebra. I mean, these are in particular R bimodules. We take the tensor algebra of this R bimodule given by the radical, and we kill the square of this generating subspace. And then this becomes a radical square zero algebra. Yes, it's defined by the same quiver, but now the product of any two arrows becomes 0, whereas in general it will be non-zero in A. And so if you like, we take A and we redefine the multiplication in such a way that the product of any two arrows becomes 0. Yes, so this is a degeneration of the algebra A. As our bimodules, they are the same, but products in A0, non-trivial products in A0 vanish. So we can view A0 as a degeneration of A, or we can view A as a deformation of A0. Yes, we deform the multiplication. The 0 multiplication for the arrows is deformed in a non-trivial way to get the multiplication in A. And so the idea would be that, well, if we have a deformation at the level of the algebras, we should have a deformation at the level of the singularity categories. Hence, a deformation also in this description of the singularity category. So the description of the singularity category via the graded Leavitt path algebra should deform into some description by some differential graded algebra now associated with A. And surprisingly, this works very well. All that we have to deform is the differential of our graded Leavitt path algebra. Yes, here the differential is 0, and it turns out it admits a canonical deformation such that we do get this equivalence. So this is a recent result by Xiao-Wu Chen and Zhengfang Wang. So we have our graded Leavitt path algebra with 0 differential, and then we can deform this differential into a non-zero differential in a canonical way, defined in terms of the algebra structure, such that for this differential graded algebra with non-trivial differential now, we still have an equivalence between the singularity category and the perfect derived category of this differential graded Leavitt path algebra. And this lifts to the DG level, and therefore we can now also compute Hochschild homology of these special types of DG Leavitt path algebras using the Hochschild complex of our algebra A. Of course, now the computation will be much more complicated because A has non-zero multiplication. But anyway, it gives us the same qualitative result. It also gives us finite dimensionality of the graded components. And I'd like to stop here. Thank you very much.
Thank you very much, Bernhard, for the nice talk. So I have 2 questions. One is the new one, and another one is a rehash of one I already asked. Say I have a graph, and I have the Leavitt path algebra of the graph. I don't know about any finite dimensional algebras, and I look into possible ways of finding a differential that makes my Leavitt path algebra into the DG algebra. How do I know? Do I have a way of knowing a priori that this will be somehow related to some finite dimensional algebra?
No, I don't know. I don't see a way of ensuring that. Yes. So your question would be which are the differentials which we can get on our algebras LA, and that is not clear at all. Yes. Yes. Yeah, I admit I haven't thought about this question, but one should definitely try to find out a little more. Yes.
Okay, and coming back to something earlier, I had asked, what about the tensor product of 2 Leavitt path algebras? And from your answer, I understood I would see this later on in the talk, but I didn't. So maybe I missed something.
Well, I mean, it is still a finite dimensional algebra, yes. And so the last part of the talk applies to it. So we can take the associated quiver, which will be which is easy to determine.
No, but I go from the other side. I have the Leavitt path algebra of a graph and of another graph, which is not finite dimensional. Leavitt path algebra is usually not finite dimensional. I take the tensor product. I have an algebra which is not a Leavitt path algebra because it has homological dimension 2.
Okay. Yes.
Then what does it correspond to any finite dimensional algebra in some way?
Let me see. You take the tensor product of the Leavitt path algebras. Yes, it's not clear. It's not clear. I mean, let me see. Yes, I mean each of them corresponds to a radical square 0 algebra, but it's not clear what the tensor product will, whether you can establish a link between the tensor product and a finite dimensional algebra. I don't know the answer to that question.
Okay. So there are some questions in the chat.
Yes.
Have a look at
Maybe
them.
the question which I had understood when you asked yours was about the tensor product of the finite dimensional algebras. And so if you take two radical square zero algebras, the tensor product will no longer be radical square zero, but it is still a finite dimensional algebra, and so it has an associated Leavitt DG Leavitt path algebra. And and I don't know whether there's any link with the tensor product of the two Leavitt path algebras associated with A and B. Yes, so questions in the chat. Let me see. A question from Quantum Joe. What is the problem for Rickard's theorem for DG categories? Well, what is the problem? The problem is that it doesn't work. I mean, Rickard's theorem says that if you have a triangle equivalence between two derived categories, then you also have a triangle equivalence realized by a bimodal. And this doesn't work for differential graded algebras, which are not concentrated in degree zeros. And then question 2, in your localization theorem, do you in fact have a recollement of unbounded? Yes, because I look at unbounded derived categories, yes, the exact sequence will be in fact part of a recollement, yes. And then, is there any result on Hochschild cohomology of Leavitt path algebras? Let me see. I mean, there are results on Hochschild cohomology of singularity categories. Let me see. Yes. So I mean, one can formulate results which relate Hochschild cohomology of the Leavitt path algebra also to computations with radical square zero finite dimensional algebras. But I don't know whether that's yes. So I would have to think about the precise formulation. I don't know whether that answers the question.
If you let me, I'll answer.
Yes.
I mean, the version Mukherjee asks, aren't Hochschild cohomologies of LPAs trivial in dimension greater than 1? Yes, but that's for the, if you do not take into account the C grading.
Yes.
Okay, so do we have any more?
Any other question?
I hear some noise, which I don't know if it is a question or. But there's one clap. Okay. So do you see anything, Gisela?
No.
Okay. So shall we stop the recording?